Very good evening, everyone, and welcome back to the session. So we have started with statistical analysis. So we'll continue with the same for today also. Okay. So to begin with, so last session we started with the basics, first moment, second moment. We talked about the mode, right? How do you apply it on continuous data, right? So the last question was, what is n minus 1, right? So why is it important that is it really important that you are changing your denominator to n minus 1? Whereas for sample, it is n minus 1. For population, standard deviation, you are calculated as capital N, right? That was the last question. So today we'll start with the next phase of questions here. So if we have the number of successful outcomes, right, expected in an experiment, infinite number of times, if an experiment is done, what is that value called as? Yeah. So let me put it on the paper here. What do we call the number of successful outcomes expected in an experiment? Yes, friends. What would be the answer? What is that value called as? So whenever you are talking about the successful outcomes, you are doing some expectation with respect to an experiment, right? That is nothing but you call it as expected value, right? It is nothing but the expected value. So the average outcome, I can say, of the experiment, whatever you are conducting for infinite number of times, is your expected value. So anything where there is a chance of getting the value being changed, when I say chance, there is a value being changed, then comes a picture of probability calculation. When probability comes into picture, there would be that is not seen, it keeps changing, right? So probability is a chance keeps on changing, it is not fixed. So definitely that time what you have to do, you have to go for expected value. You are expecting something, right? So usually when you take like something like bonds, right? You have government bonds, you have stock market. So what happens? Things keep on changing for stock market, right? Once you just put some amount, right? It keeps on changing. It is not the chance of getting it raised, the chance of getting it declined. It's equally there here, right? So what happens if you compare it with a government bond? If they say that it is 8%, it is 8% throughout, and they don't increase it or decrease it every month. The amount, whatever you, if you have invested 100 rupees, right, you get the amount back. 8% means you get it 108. So what happens here? The thing, whatever you are putting here, you are investing, is fixed. There is no question of expecting there. Normal mean is a normal mean. So expected value is nothing but you are calculating the mean, right? It is nothing but the average, right? But when it comes to the chance or getting the probability value, the chance of changing it, right? When you perform any infinite number of times, you're expecting something that is nothing but your expected value, right? That is your expected value. So when you talk about mean, we talk about what you call it as median, mode, right? So there are few notations also respectively, right? Can you show a difference, right? Or what is the difference between the population parameters and sample statistics with respect to sample deviation? Or you can give a notation of standard deviation for a sample. Yeah. What is this notation? So when you talk about parameters, when you talk about parameters and statistics, right? You have to know the difference. When you talk about population parameters, when you talk about the sample statistics. What would you get? So population parameters, if you talk about sample, right? Sample means you are working, the results what you get, you call them as sample statistics. So S is what you denote for standard deviation, right? S is what you denote for standard deviation. Got it? Now, whenever you take, right, outliers or you talk about some extreme values in your data, definitely this will change or not? Due to outliers, your values get changed? Definitely. But my question would be, how do you identify these outliers? How do you identify these outliers? Yeah. What is the approach to identify outliers? Identify outliers. Box plot. Okay. What are the other? Many are there, right? Other things. How do you do? Only box plot? One approach? Exactly. Checking the skewness. So first thing is that you can check your mean and median values, right? We can also go for symmetry. You can check the symmetry of your data, right? Through histogram. Yeah, the IQR range. Exactly. Right? Then what you have answered, that is a box plot. Right? And also you have, what else? A kind of plot, other plot is also QQ plot. Right? So statistically, we can also say that skewness, right? No, how do you handle them now? Yeah, exactly, Praveen. How do you handle them? Simply, you can't say that you want to remove them, right? You can't do that. So, what approaches you would think of when you find such outliers in your data? So, it becomes important sometimes, right? So, you have to handle them depending upon the cause. First thing, right? Depending on the cause, you would handle them. If it is very, very important for us, you do retention of that particular data point. Yeah, replace them with, very good. You replace them with mean and median, depending upon the type of data you have, right? Mean and median. And remove is what you have to do with the last option, right? What is the other way? Can you do a normalization of the data? Can you do a normalization? The outlier analysis treatment. How do you do that? What techniques do you have here? Next. So you can also do something like, you would exclude those points which have large influence, large degree of influence on estimated coefficients, right? Remember Cook's distance? You remove them, right? Whichever is crossing the line. Yeah, exactly. 3R technique, trimming, Winsorization, right? You rectify, you retain, you remove, right? So when you have millions and millions of records, what will you do? You just do a plot, the famous plot that is nothing but your box plot, what we have just now written. Right? You take all the outliers, make them as one data set. Right? You do the box plot like this. If you have the data points, all these data points would be becoming your data set B. This would be your data set A. Yeah, box plot. Right? So this is one way. Now we have told Winsorization. Now what is this Winsorization is? What is Winsorization, friends? Winsorization, trimming, anything. Trimming. So Winsorization, you don't delete any of the data points, right? In Winsorization, there is no deletion of data points. You try to find the 5th percentile and you also try to find 95th percentile. Right? I mean percentile. Okay, not percentage. 5th percentile. Exactly. So 95th, any value which is above this particular line, right? If you take this as your 95th percentile and this is your 5th percentile, right? Anything which is above this, you force it and you bring it to 95th percentile. Anything which is below this, you force it and you bring it to 5th percentile, right? This is called as Winsorization, right? So what is that trimming then? You understood that in Winsorization, there is no deletion of records is happening. Will trimming also do something like this? What is trimming? Trim. The name itself, you can understand that trim. Right? You trim the lower 5%, you trim the upper 5%. Right? You start working on whatever you have it in the, this is your median. Trimming taking, where you have 5%. You trim 5% of the data. Lower 5% you trim off, upper 5% you trim off. Whatever is left out, you work on the data. Trimming means you remove them. So deletion is happening here. You do deletion in trimming. You don't do any deletion in Winsorization. Right? So that is how you have to say. Your all answers are correct, right? Your 3R technique, Winsorization, swamping, masking, right? You do box plot, everything to find out the outliers, whether they are important or not, analyzing. That is very, very important because they may be important for us, because this is something which even talks about the skewness. Long tail products are also important. Okay, next. To measure the degree of asymmetry, right? To measure the degree of asymmetry, which is exhibited by the data, what do we have to use? Yes, friends, tell me. To measure the degree of asymmetry, whatever is exhibited by the data, right? What do we use to find that degree of asymmetry? Yeah. Simple. Asymmetry. Exactly. Yeah. You do skewness, right? Skewness is something which helps you to find out the degree of asymmetry in your data. So if you, okay, I agree that yes, skewness, but what methods do you have to handle skewness? Skewness is correct, exactly. But what methods do you know? Tell me. What do you do to handle skewness? What methods do you take? To handle the skewness? Yes. Histogram also will help to know the skewness. Good. So that's why I told you degree of asymmetry, right? The number. So skewness is a correct answer. Now, how do you handle this skewness? Okay. You can do normalization. Question mark? It is not normal, right? If you have skewness in your data, it is not normal. So if the data are not normal, what you have to do? The data is not normal. You can go for log transformation. You can go for square root transformation. You can go for Box-Cox transformation, right? To reduce, to make data normal. Transformations, right? So you know the answer. What methods what you do? You go for transformations. Many type of transformations are there, right? Depending on that, you take a call. So which is reducing the skewness. So you know what is log? Yeah. So it works with a lambda value. Box calls works with a lambda value. Optimum value is what you have, your data is will get selected to. Right? If your lambda value is not equal to 0, if a lambda value equal to 0, your equation y of lambda would change. Let me write down. So when you have y of lambda, you have y of lambda minus 1 by lambda if lambda is not equal to 0. You have log of y if your lambda is equal to 0. Right? So this lambda value may vary from minus 5 to 5. All the values of lambda are considered and the optimum value for your data is what you select. So what is the optimum value? It is a one which has the best approximation of getting a normal distribution curve. So the transformation of y with respect to box Cox would be this. Right? This is the what you get it. So when we are talking skewness, good. What is this shape statistics all about? What are shape statistics? Yeah. Shape statistics. Do we have something to do with shape? Any statistics related thing? Questions. What are shape statistics? Okay, skewness and kurtosis are called as shape statistics, right? Where it helps you to find out with respect to shape, you are able to take some decision on the sample data, right? Skewness can be positive, skewness can be negative, or skewness can be normal also, right? Even kurtosis also comes into picture with shape statistics. Kurtosis is your fourth business moment decision. Skewness is your third business moment decision. Right? Depending on that, you segregate them. Right? Kurtosis is equal to 3, right? Greater than 3, less than 3. Leptokurtic, mesokurtic. Right? Now, if I ask you if mean if your mean is greater than median, how is the shape? What is the shape of the curve? What is the shape of the curve? So mean being greater than median, the shape would be positive skew. Right? The data is asymmetric. Right? It is also called as, understood as right skew. Right? Exactly, Kiran. Yes. So the mass of the distribution is concentrated on left side. So mass distribution is on the left side, so you call it as a right skew. So can someone give me the best example for right skewed data? Example for right skewed data. Mean is greater than median, agree. The distribution is right skewed, agree. What's the best example you can give? Anything which is. So tail is on the right side. Any example you can think of. Any supermarket data, right? Any e-commerce where you have which stores the data like Amazon, eBay, etc. Right? That was the best example because you have the products being sold, not every day, same products, right? There you have long tail products also. Okay, then what is this mode skewness? You know there is something called as mode skewness. What is that? Yeah, exactly, Kiran. So what is this mode skewness? So Pearson's first skewness coefficient is called as mode skewness. Pearson's second skewness coefficient is called as median skewness. Right? You have the formula for that. You have the formula for that, right? Mode skewness and median skewness. That is mean minus mode by standard deviation. Right? This is your mode skewness. You have median skewness. That is nothing but we call it as median skewness. Exactly. Right? So this is Pearson's second skewness coefficient. Right? Pearson second skewness coefficient. This is your Pearson first skewness coefficient. Okay, what is the use of kurtosis? You know that kurtosis is something which talks about the peak, right? How is the peak, and you know that you have wider tails or you have wider peaks, thinner tails, right? Heaviness of the tails is what you are observing. But what is the exact use? What is the other use I can say? Kurtosis. What else can be captured? So kurtosis basically is a fourth moment business decision. Exactly. So you have wider peaks, right? You have thinner tails. So it's something like this. Yes, you all know. It could be like this or it could be like this. Sometimes no tail also. Right? There are no tails. But here you have wider tail. This could also be like this. Chance is there. Outliers, not really. It is used to find the size of sample data set. The size of the sample data set. So n could be greater than right n value. So you can even find the sample. Yeah. Now someone earlier answered IQR. What is IQR then? What do you talk about IQR? IQR is something, it talks many things. IQR is your interquartile range. So if I ask you IQR is interquartile range, yes, good. But what is the fifth percentile of the data can be referred to as? What's the fifth percentile of the data? What do you refer to as? 50th. You're talking about IQR. Very good. This is your box plot. And this is your interquartile range. Out of this, what is this line? That is the answer, right? It's a median. 50th percentile of the data is referred to as median. Okay, we are keep on drawing box plot. What is the primary purpose and secondary purpose of box plot? What's the primary and secondary purpose of box plot? Yes. Exclusively only for outliers or something else also? The primary purpose is exclusively you will take for outliers, the shape of the distribution. Very good. Okay. So what happens here is when we talk about box plot, first thing is outliers only. If you want to check outliers, then the secondary purpose would be spread of the data. How is the spread? Where you have the more concentration of the data, where you have less concentration of the data. So do you think there is some criteria to calculate outliers? Box plot follows some criteria to calculate outliers. What is the criteria being followed to calculate outliers? Anything which is above the lines what we are keep on drawing, right? There should be some criteria. If you write like this, you have Q2, you have Q1, you have Q3, you have Q4. Yeah, few books use 3 times of IQR also. Few books use 1.5 times of IQR. Exactly. They use 1.5 times of IQR. Which is something above this. Right? This is how you calculate your outliers. To count outliers in a box plot, right? You have dots. Is these dots, every dot represents one outlier? If not, how do you do that? How do you assign it? How do you find outliers in the box plot? So to count outliers in a box plot, you should assign a variable to it. Right? You assign a variable like this. Box plot of any variable, you assign it. So it would give you as out. A would be given a list of 6 elements. In that you'll get out, which would give you the number of outliers, and also you get the length of your outliers also. You can even find the length of the outliers also. Right? Very good. Now we are talking about skewness, kurtosis, normality. What is this normal distribution then? What is normal distribution? Why are you assuming that everything is normal? What is normal distribution? This is also one of the important probability distribution as a part of statistics, right? You have height, you have blood pressure, you have error measurement, you have IQ scores, many things, right? So you also call it as a, whenever you feel that the data is normally distributed, it would be a bell-shaped curve. This curve is also called as bell curve, or you also call it as Gaussian curve. Gaussian distribution. Normal distribution also called as Gaussian distribution. Right? What are the properties of normal distribution? What factors should satisfy so that you call them as normally distributed? The data is normal. Or data are normal. Properties. Exactly. Very good. So despite of different shapes, right, all forms of your normal distribution should have some characteristics, right? So what are characteristics? We assume that everything is symmetric. Exactly. You have the normal distribution where you say that mean is equal to median is equal to mode. Very good. All are equal. So half of the population is less than mean and half is greater than mean. You have some empirical rules. Yeah, the range is minus infinity to infinity. So the empirical rule allows you to determine the proportion of values here. Right? The proportion of values, so which fall within that particular distances from the mean. So definitely it would not fit all the population, but it is, yeah, skewness is 0, kurtosis is 3. So normal distribution is basically characterized by what factors? Normal distribution is characterized by what factors? Two factors are very, very important. Mean and standard deviation, right? Normal distribution is characterized by two factors, that is your mean and standard deviation. So do you have any plot for finding out the normality of the data? Right? Anything which is there to understand whether the data is normal or not, other than whatever we have discussed till now? Shape and spread given by mean and standard deviation. Exactly, right? QQ plot. QQ plot is what you would consider. And that also, when you try to draw a line, this is your interquartile range. Maximum data points should fall on this line. And the line, whatever you are taking, should be linear. Right? It should be linear. Linear means for any change in X, there should be change in Y. So in your box plot, this region, whatever you do, right, this is also holds good for finding out the normal distribution, but exclusively we have QQ plot to check whether your data is normal or not. So because we are interested in QQ plot, only it is doing a comparison with standard normal distribution. Right? We are going for standard normal distribution. Exactly. So now for a standard normal value, the value of mean would be, you said QQ plot talks about, it just does with changes the value to standard normal distribution. Right? QQ plot. Right? It's correct, exactly. It compares with the standard normal thing. So there should be some normal variate, right? For a standard normal variate, the value of mean. Yeah, tell me. So the mean would be equal to 0, standard deviation would be equal to 1. Then you call it as a standard normal variate. Right? Okay, very good. So what are the assumptions for statistical tests? Whenever you're doing statistical tests, what assumptions do you take into consideration? If you just go deviated from the assumptions, what is going to happen if you violate them? What are the typical assumptions? What are the assumptions for, let me write it down. Yeah. Okay. Correct. Data should be normal. Next. Data should have linear relationship. Data should have normal distribution. Right? At least it should be symmetric. And the data from multiple groups should have same variance. Right? Something what we call as homogeneity of the variances, normality, and linearity. Right? When these assumptions are violated, you would be misleaded, or completely our analysis would go, it would go in a wrong way. Right? Yeah, what is a standard normal distribution? How do you represent that? We're talking about standard normal variate. No, how do you represent that? Yeah. How is standard? It's not deviation. Normal distribution represented. Yep. So what are the applications for the scaling function? Exactly, it's Z, right? You represent as Z. Very good. So what applications do you have? What is the formula actually for Z? X minus mu by sigma, right? So we are transforming your values, X axis to Z values on the same axis. Now what other applications do you have for scale function? What are the we will write of scale function? What are the applications for scale function? So you need to do standardization, right? Why you want to do standardization? You want to make it all the data points should come to same level. So all the variables would be under the same scale. So what you have written is that, yes, normalization. No, I'm talking about, yeah, okay. It is 0 to 1. Very good. When you do normalization, the values would be between 0 and 1. So when you do scale function, you are converting the mean equal to 0, sigma equal to 1. Data is becoming unitless. Right? We can even do standardization for what purpose? You are able to find out The probability of a continuous random variable. Why? Because we cannot calculate for single variable. Right? We take a range which is none other than the area under the curve with integrals. Right? You do it like this, right? You take the integral, upper limit, lower limit. We calculate the integrals. Right? Upper limit, lower limit. You calculate the integrals. So using z, we also get the probability of a random variable. I can say continuous random variable. So what is the reference variable which is used for comparing all the variables here for normality? With what you are comparing? All other variables? Which reference variable you are talking? We can calculate probability over range using z values. So the reference variable what you are talking, right? You are taking other variables. Other variables means x, any variable which is other than, it could be anything. It is compared with standard variable for checking the normality. Right, so properties of z distribution will be mu will be equal to 0, right? Sigma will be equal to 1, identically distributed, and it is symmetric. So you're converting your x to z scale. That's why you're calling it as z is equal to x minus mu by sigma. Yeah, now we have written normalization. What is the difference between standardization and normalization? Is there any difference? Can you apply both at a time? Right? Standardization and normalization. The terms, right? You can use them either way, right? You can go for normalization or standardization. No one is stopping us. But what is the major difference? What will happen if you do apply standardization? What will happen if you apply normalization? See, these refer to different things. Both are different. So normalization means usually it means that is used definitely to scale a variable, and you scale a variable in such a way that the values would be changed between 0 and 1. The values, whatever x value you have it in your data, that gets changed to 0, between 0 and 1. Normalization. Exactly. So standardization, what it will do, it will transform entire data. Transformation is done in such a way that if you do mean and standard deviation of that particular transformed data, you get 0 and 1 respectively. Exactly, Kiran and Suraj, right? It would give you a value, mean would become 0 and standard deviation would become 1. Right? So you can apply either both of them and check, build a model, or you can go for one option. Right? There is no like criteria that only normalization should be applied or standardization should be applied. So what is the central limit theorem, friends? When we are talking about normality, the next thing would be where you use the real-time application of central limit theorem. Where it exactly used? Euclidean distance algorithms, we are never restricted our calculation for Euclidean distance. Right? You have many kinds of types of distance calculations, but still, yes, you can opt both and work. Whichever gives you the best accuracy, best model, least errors, right? You can go with that. Central limit theorem, very, very important. Central limit theorem. Remember, theorem is theorem, right? Sun rises in the east. How do you explain that with real time? Where you are using it in real time? Why it is required actually for us? You have so many techniques, we have so many assumptions, but why? The answers, when you are applying it, is it important or not? Okay, so whenever you are talking about central limit theorem, it is used for, first thing is inferential statistics. So it is an only theorem, right? You are doing an assumption here that the data is normally distributed. Why are you using this? Because we want sample for our analysis. So samples taken for analysis definitely would vary. You would take one sample, I would take one sample. Right? It keeps on changing, right? So here the point comes into picture is a point estimate. Right? The point estimate what we calculate will not be the same for all the samples, right? Your sample, my sample, any other sample. So the samples, whatever the statistics means whatever you have worked on sample data with respect to different samples would be not same. So the inferences definitely will change. So what does the theorem assumes? Theorem assumes that the sample to be normally distributed, right? So that it will allow us to capture the variation in this particular point estimate. So we assign that particular value, right? We take that particular value for population. Right? There are two statements, most famous statements for the central limit theorem. I want them. Can someone state them for central limit theorem? Yeah. So we get something like average of averages. What is that average called as? The distribution of the sample statistics will be normal irrespective. So what is that actually? Whenever you talk about the data being normal, right? We know that if the population data is normal, the sample data is also normal, right? But if the population data is not normal, still you assume that the sample data would be normal if you have a very huge sample data, right? You take huge number of samples, then that is, those two are what you have to follow. When you increase your sample size, there's a chance that your data would become normally distributed. Why? Because here you have the variation in the data. One data point, how far it is being deviated from the center, you are calculating the standard deviation. That is the average deviation of each data point from the center. So that whatever you are doing the calculation for sample mean, you get some result. That result is nothing but the sample mean result is nothing but you call it as a point estimate. So you even estimate your population value by using that particular same result. But how much is the deviation? What is the variation you are getting from the population value? How far you got deviated from when you predicted something? Right? Sample 1, you will be deviated from some data point. Sample 2, you would be deviated from some, right? From the original data. Here also you find some deviation here from this thing. So that deviation is called as what? Standard population mean. Okay, yeah, very good. That is nothing but, okay, you have come in that thing. Margin of error. Fine, let me write that deviation is nothing but your so it's nothing but you write it by sigma by root n. So population standard deviation by root n. So usually if you have line like this, if this is your x bar, this deviation is nothing but your x1, x2, right? To be like this. This is for sample, right? So when you compare with in other way, you have this mu, you have here x1 bar, this is your x2 bar, this is your maybe x3 bar, these values. So here you get an error, the deviation you call it as sigma by root n. We are predicting mu value using these values x1 bar, x2 bar, x3 bar. When we take the average of all these deviations, we are getting the standard error of mean. So total predictive analytics revolves around this, right? If I take average of all the errors for multiple samples, that is becoming your standard error. Right? That is a difference for what you have to capture for central limit theorem. It's very, very important. So usually what happens whenever your data is not normal, what would you do? You should make it normal. Right? That's why we have to go and take more number of samples here, so that there's a chance that the sample increases, your data becomes normal, though your population data is not normal. So here average of averages or mean of the sample means is called as what? Mean of the sample means. Just now I told you. Mean of sample means. You are getting x1, x2, x3, right? Let me put it as capital. You get a population mean, right? You get a population mean. So what is the minimum sample size you are considered to be good enough? What is the minimum sample size? Is it fixed? Is there any criteria to check that? Minimum sample size? Basic, normal value. Minimum sample size. Yeah, anything which is greater than 30 is considered as the sample size. Very good. Okay. Now, when you talk about the predictions, we are doing some predictions, right? Can we trust on single value predictions, single sample predictions? Can we trust on single sample predictions? Yeah, single value prediction. No, right? Because as the sample keeps varying, we cannot trust single sample prediction because the results will be changing to various conditions, right? Due to various conditions. So maybe the sales of one quarter would not reflect always, right? So you are talking about margin of error. What is margin of error? Formula? How do you write that margin of error? How do you write that? So margin of error is nothing but you have z 1 minus alpha, right, into sigma by root n. Now what is alpha here? What is alpha here? Alpha is nothing but your significance level. It is called as error or significance level. The probability of the error is 5%, which is nothing but 0.05. The chance of going wrong is accepted only till 5%. If it exceeds, results would change, right? So if alpha is equal to error, you have 1 minus alpha, which is nothing but your confidence. Right? 1 minus alpha is your confidence. So 1 minus alpha would become 95%. Right? So the MOE, what you call the margin of error, is always associated with some confidence, right? It is associated with some confidence. It could be 95% or it could be 99%, right? 90%, right? So you have the z values which you have to remember always at 5% significance level. Z value at 5% significance level. Z value at 5% significance level. Right? It is 1.96. Right? It is 1.96. So finally, what is the difference between z test and t test? When you are going to use z, yeah, 1.96 exactly. When you are going to opt z, when you are going to opt t. Yeah, the difference between z test and t test. Do you have any difference? Z is having 1 minus alpha only, right? Z test holds only 1 minus alpha. But when you go to t-test, there is again degrees of freedom coming into picture, right? So when population standard deviation is known, you go for z-test. When you don't have any information here, then you go for no information is there, then you go for t-test. It depends on also on sample data, right? How do you select your sample data? Also, there is an option of choosing. Exactly. So you have students T distribution and Z test, right? So whenever you have a huge sample, when n is tending, n is very, very huge, your Z would follow the same as T would follow same as Z, right? If your n is very, very, it's increased, the sample size is being very, very huge, then your T would become Z, right? So you opt Z test when you have some information about the data. That is, sigma is known to you. If sigma is also not known to you, you go for t-test. So here also you get a confidence interval because you are adding up with your point estimate plus or minus margin of error. So which one should be wider? Which interval, if you go for z-test, would be wider or t-test output would be wider? Understood my point? When you are going for z-test, you get an interval. When you go for t-test, you will get an interval. So it depends upon your point estimate plus or minus margin of error. Right? The formula is same. Here you are using z1 minus alpha, right? It's 1.96 into sigma by root n. Here you use z1 minus alpha and n minus 1, right? Sigma by root n. Point estimate is again common here. Which value should be more wider? See friends, if I just give you, I want you to predict tomorrow's temperature. So when you want to predict tomorrow's temperature, I give for person A and B, two people, I give the data. For him, I give yesterday's data, I give him satellite images, right? I give him some kind of data, whatever I have, satellite images. Okay. Here for B person, I give only look at the sky and tell me. So the interval what A should predict, right? And what B would predict, there's a lot of difference. The same with t-test and z-test also. Z-test is not having any information. At least t-test is not having any information. Z-test at least is having sigma. Some information is there. So this prediction could be nearly equal to your original value. But t-distribution is not having any information. He should look at the sky and give you an interval. So t-test values should be more wider. Like he should give a prediction like saying that 24 to 34 tomorrow data, because it should be more wider. But when it comes to z-test, he should give an interval of very near, right? He should give like exactly 30 to 32. Right? So that is how you have to analyze it, because z-test is having at least information of sigma. If that is also not known to t-test, right? This should be more wider when compared to z-test. Okay, so we'll stop here, right? Thank you so much, everyone. Hope you have recollected few things. Right? And we'll reconnect next week, same time, right? With a different set of questions. Thank you all.